Okay, so I'm going to explain the impulsive function, and that's Dirac's delta function, all right? So the beginning is this. You remember? What is it? The square function, right? It's 0 everywhere except a to b. That's square function, right? What if we make it very short? Short duration. It's like impact, right? Okay? That's the idea. So we are building a square function. We're going to redefine the square function, and we're going to make it very narrow but high function, okay? Very narrow, very tall square. That's what impulse is, okay? All right. So we start from here. Okay? Instead of defining B, we make, this is A, and A plus K. And the height is 1 over K. We start from that function, okay? To make that short impulse. Okay, so we define function sub K, okay, of T minus A to be 1 over K from A to A plus K, 0 otherwise. Okay? This picture is exactly mathematically you can write this way. One more thing is, one thing is, this is really, really important. This is the way it designed. It is designed, okay? So area is 1. Then if you can, I mean, here this is K, right? K times 1 over K is 1. So this square function is designed to be area to be 1. Why? Why? If you want to define a new function, unity, 1 is really important. Having 1 means you can divide by something, right? You can go back to yourself. So unity, the 1, is really important concept for the mathematical function. He wanted, Dirac wanted to make the unity as an area. This is very brilliant, okay? So that, and then he suggested K goes to 0. Okay? Because the impulse is really narrow happening, right? Okay? So it means if you go K to be 0, look at this, what this curve happens. So K is reduced by half, let's say. Then the tall, because to make area to be 1 all the time, the height has to be doubled, right? Even 1/4, this one has to be grow very high, right? And if you make it even narrow, that goes to infinity. That's the basic of this short impulse. And all right, so let's define formally Dirac's delta function now. Okay, so you are ready to define Dirac's delta function. Okay, so we use Greek letter delta. I mean, Dirac used this Greek letter delta as a function name, and T minus A, which is limiting process, K goes to 0, the f sub K T minus A. Okay? Then it's infinity at T is A, 0 otherwise. Right? If we draw this function, that's exactly this. Correct? That's the delta function. So remember that. One more property is this. Shifting property. Wow, shifting again? All right. Shifting, shifting, shifting. Laplace is really good at shifting, okay? What is it? What does that mean? G of t, delta of t minus a dt is g of a. All right. Let's draw it again. So let's say we have function, a function, right? Any function, okay? And a is here. Then that's delta Dirac. Dirac's delta function, right? Then what is it? It's g of a, right? Else, otherwise 0. It's only some value exists here at a and otherwise 0. Okay? So it's like infinitesimal shifting. It's like, let's say b, we have another delta function, right? And we have another, function like h. This is what? H of b. So let's take a Laplace transform of the delta function. So we start from f sub k, naturally, right? Because that's what we started to define the impulse function, the delta function. So we start from this. That's u of t minus a plus k. Correct? Using square function, yeah. There's nothing but square function of this. Okay? So this one is using the square function. Okay. So we do the Laplace transform of this, f sub k. Then from 0 to infinity, e to the minus st, 1 over k times u of t minus a minus u of t minus a plus k dt. Right? Just definition. It's 1 over k. So we take the 1 over k out, and we divide the two terms, e to the minus st times u of t minus a dt minus 0 to infinity, e to the minus st, u of t minus a plus k dt. Okay? I'm just rewriting it. It's nothing. Then it's 1 over k. This is the definition, right, of u of t minus a. So e to the minus as over s minus e to the minus a plus k s over s. Okay? And this is e to the minus as. If we reorganize it, that's what it is. E to the minus ks over ks. Then the delta function is what? When k goes to 0. That's the delta function, right? So we can formulate this like this. So limit k goes to 0. The second term, ks over ks. Okay? So limit k goes to 0. So here, the first term has nothing to do with k, right? So we can only, do that limiting process for the second term, and that's what it is. If you plug k to be 0, this e to the 0 is 1, so 1 minus 1 is 0, right? 0. 0 over 0. What do we need? Okay. So if you do that, So limit k goes to 0. If you differentiate that, e to the minus ks over s. Okay, 1. Right? Okay, the second term is 1 here as k goes to 0. So Laplace transform of delta function is actually limit k goes to 0, Laplace transform of f sub k, t minus a, and that is as. Okay? You remember u of t minus a was e to the minus as over s. Right? Delta, there's no, division of s. So example 1. It is actually square wave input, square function input. Okay, this problem is. So y double prime plus 3y prime plus 2y is r of t is u of t minus 1 minus u of t minus 2. And all the initial conditions are zeros. Okay. This is a square function, right? So input term is square function. All right. So s square plus 3s 2y is 1 over s e to the minus s minus e to the minus 2s. Okay, so y is 1 over s plus 1 s plus 2 times e to the minus s minus e to the minus 2s. Okay? And we define this term to be f of s. So it is multiplying exponential function to the f of s, right? Then it is what? Shifting in time domain. Okay? We are using shifting right away. Okay. So f of s is partial fraction, this 1 over s plus 1 plus 1/2 over s plus 2. Okay? From the partial fraction. And f of t, we can easily get that inverse Laplace transform of f, which is 1/2 minus e to the minus t plus 1/2 e to the minus 2t. Okay? But you have to remember, this is not the whole y, but part of it. This is the f function that has been shifted. Okay? Now, y is the inverse of f of s times e to the minus s minus f of s times e to the minus 2s is actually the function has been shifted 1 and 2. Okay? So far so good, right? So to express, so what is it? T minus 1, f is this, right? So we put t minus 1 to all the t's, right? We put t minus 1 instead of t. Okay? And t minus 2. Yeah, for your understanding, probably I'm going to write it. So that's f of t minus 1 is what? 1/2 minus e to the minus t minus 1 plus 1/2 e to the minus 2t minus 1 times u of t minus 1. Okay? Minus f of t minus e to the minus t minus 2 plus e to the minus 2t minus 2 times ut minus 2.